let's start. I'm working on IMD heterogeneous system architecture compiler, and I'm sorry. Okay, and partly this work related with HSA, and part of this work is pretty general. Starting to talk about the new optimization technique, it's a good idea to explain why do we need it for. Now we know there are a lot of massively parallel hardware platforms and wide range of high-level source languages that provide their own source-level parallelization means, like OpenMP provides pragmas, OpenCL provides so-called computational grid, a set of intrinsics that can answer how many dimensions we have, what size of each dimension, and so on. To make hardware leverage on that parallelism, we need to be able to employ as many vector units as possible, to run as many threads in parallel for data processing as possible. In this picture, vector registers become like critical resource. Let's say we have a large data array to process. You would like to employ as many vector units as possible to process array chunks, like 64 elements in one cycle or so. But for that, we need enough available vector registers. And let's imagine we don't want to process the whole array, but the array slice. And let's imagine we have to compute the start and end indexes for the array slice. And if this computation is a large arithmetic expression, if we use the vector units for this, you would operate on the vectors with the same elements. If you put scalar into vector, you will get like vector of equal elements. From the point of resources, it's just wasting the registers. So idea is to split the data flow of the program in two parts, the vector one and scalar one, to save the VGPRs, vector registers, for those instructions that can leverage on them. This optimization consists of two parts, the analysis and the transformation itself. The analysis is pretty much general and can adopt a wide range of parallelization paradigms. But transformation is very much OpenCL specific and HSA specific. To abstract from the concrete hardware, let's consider the abstract parallel machine. It has several vector units and scalar units. Vector units run a wavefront. Wavefront is like a group of threads executing same instruction on different data. Vector unit operates on vector registers. Each vector register consists of n, let's say 64 equal lanes of 32 bits. Each thread operates on its own chunk of that data. Also, we assume that broadcasting scalar value to the vector lanes is cheap. We have two kinds of memory in our abstract machine, the private memory, that is dedicated memory for the thread. No other threads can access the thread private memory, and shared memory that are common among the wavefront. In fact, in IMD hardware and in OpenCL, we have also the notion of thread groups. We can split the wavefront to several thread groups, and we have common group memory. But for abstract machine, we stayed for private and shared. Also, we assume that any two threads, if they access the same effective address, they would access the same value. And the last assumption that scalar and vector data cache are not coherent, so vector write would not invalidate according cache line in scalar cache. Here we introduce the notion of uniformity. Any vector operation, vector operation has vector operands. If all lanes of vector operand contain equal values, we say that operand is uniform. All operands of which are uniform is considered to be uniform. It produces a uniform result. The idea is to analyze the IR and to find all uniform operations and change vector operations to scalar if operation is uniform. We are saving VGPRs. One more benefit is scalar cache. For example, in AMD hardware, 6 times faster than vector. And one more is opportunity for instruction scheduler to saturate scalar unit, maybe achieve more effective schedule. Here is this slide explains some OpenCL specific part. Because of cache, scalar and vector caches are not coherent, we require the so-called constancy property of a data. It may be just constant memory, or it may be proven to be not written over all passes from the entry block to the point of interest. So we employ trace analysis, and I had to develop my own HSA-specific alias analysis pass for that. The analysis is really LLVM model pass over the LLVM IR. It accepts the LLVM IR and produces the IR attributed with 2 kinds of metadata. Each instruction is attributed with so-called width attribute. The width is how many threads accessing, executing this instruction will have equal uniform operands. For example, the width of 1 is that this is a naturally vector operation. So only one thread accesses equal data. Each thread accesses separate. If we have a width of all, that means that it's a scalar operation, and every threads would access same value. And also we have group. So all the thread group access same value. And and the second attribute is constancy. It's a Boolean. Here is the optimization has some restrictions. Part of them related with AMD specific and OpenCL specific, and another part related with the LLVM infrastructure restrictions. Okay, in AMD HSA compiler, we have really 2 compilers layered in a stack. The high-level Clang and LLVM-based compiler accepts the OpenCL and produce HSA AL, heterogeneous system architecture language. And low-level proprietary compiler, so-called finalizer, accepts the HSAL and produces the GPU ISA. So we have to pass information that we collect over the IR. We have to pass this information to the machine code. Currently, LLVM has no convenient means to pass user-defined metadata through the instruction selection. So we only can pass these attributes for memory instructions because they have memory operand and the specific metadata. So we use this metadata to pass uniformity attributes to the machine code. So that's why we just, in current implementation, cannot scalarize any instruction, just loads, because the most resource-consuming, time-consuming operation, vector loads. Okay, which source of non-uniformity we have. One is explicit. In OpenCL, we have well-known set of the intrinsic. That intrinsic describe computational grid dimensions and thread ID within the dimension. So the only source of the set-specific data is the set of these intrinsics. Data dependency is trivial because reflected in SSA explicitly. We just here there is use and there is a definition that like non-uniform operation defines this operand. So this is trivial. And if you traverse the SSA graph, slice of SSA graph, we eventually reach the non-uniformity point and understand that the whole slice is non-uniform. Stepping a bit forward, all the analysis may be thought as a backward program slicing from the point of interest over the SSA graph until we reach the kernel parameter or the literal constant, or any constant value, because every constants are uniform and kernel parameters are uniform by default. So if slice consists can contain at least one non-uniform data, the whole slice is non-uniform, and the slice root, the instruction of interest, is non-uniform. And another source is control dependency. Let's say we have a branch, and we have two paths of execution, and same variable assigned different values along this path. And then we use this variable. There is no explicit data dependency that may be reflected by SSA. So we need some tricky things to account this. Okay, this is just formal description of the analysis. Really, we have the partially ordered set of three elements, trivial semi-lattice. This partially ordered set are restricted. It has bottom element, it has top element, and we define width of operation as minimum over all its operands with. Because the minimum function is monotonic, set is restricted and ordered, our iterative analysis proved to reach fixed point. Okay, and we also define the set of, okay, as I said before, constant value, always uniform, kernel argument, always uniform. And we define the set of operations that are known to be non-uniform. In real analysis, we have like predefined set that always group with, that provide a result of with group. Now for simplicity, we just not mention it. At the start of analysis, we initialize known as uniform. Okay, we put all the function body instructions in a work list in execution order. And we initialize that instructions that known to be non-uniform with bottom element, and we initialize all other with top element. So this is a classical iterative solver over the SSA. The iterative analysis is forward because we are propagating the uniformity property forward along the backward slice. Okay, how we deal with control dependencies? and what really control dependency is. We say that if some instruction is executed along one path of a branch and is not executed along another path of a branch, this instruction is control dependent of a branch. We treat control dependencies as a post-dominance frontier sets, like was introduced by Cooper. And we use classical Cooper's algorithm. He published this algorithm for computing like dominance frontiers, but we just use post-dominator tree instead of dominator tree, and so compute post-dominance frontier set. Okay, here just some formalizing. Okay, let's say if we are interested in the point of a program where the 2 or 3 or many values merged, the value merge point explicitly reflected by SSA by means of phi functions. But in any phi function is the definition itself. It can define the operand of another operation. So eventually, iterative solver would process the phi function as an operand for another operation. When we encountered phi function, if we only consider their operand and compute phi function with as a minimum of phi function's real operands with, we wouldn't account for control dependencies. So we just add to this phi function operand set all branch operations of which this phi function control dependent. And then we process phi function as normal operation. Here we use set difference between the parent block of a phi itself and a parent block of operand. Here is this union over all operands. Next slide will explain why we do so. Let's consider counterflow graph. If we're interested in a weight of the control dependency set of this definition. Okay, the first parameter originated from the block 8. The 8 block post-dominance frontier consists of block 3 and 2. Parent block is 5. The 5 post-dominance frontier is only block 2. Let's say we have non-uniform divergence here. Let's say 10 threads go block 3 and another block 9. All 10 threads that will reach block 5 will execute or 8 or 4. So the reaching definition here is 0 or 1. So we are only interested in these 10 threads computing weight and control dependency set for this definition. So we shouldn't account for this condition, only for this. That's why we use set difference. Putting things together, the analysis is the analysis is interprocedural. So we walk call graph in a post order. Thank you. So that we can ensure that the Kali body is processed before the caller body. So when we encounter the function call, the uniformity of function returning result, returning value, already has been computed. One pitfall in these function calls is what will happen if we if we pre-compute function Kali body, and then we processing the color body, we understand that we pass the non-uniform result to the Kali. In this situation, we have to recompute the Kali, obviously, because we're treating, by default, we're treating parameters as uniform. This is not the case, so we have to recompute. I'm sorry. Same things with by reference operand, where ZV pass and that can be changed non-uniformly in the Kali body. If we prove that they change it in non-uniform way, we have to employ alias analysis to understand which other pointers may be non-uniformly changed in the color body. Some examples. Simple OpenCL code, not very meaningful, but just for example. We have, obviously, non-uniform load and two uniform loads. Here is just ControlFlow. Here is it. I tried to explain what is really the SSA graph and graph slice. Here is our load. The only its parameter is definition. Definition parameters. One immediately stops because it's kernel argument. And from the second one, we go on until we reach the constant or another parameter. Here is a slice. This is a backward slice that only contains instructions that contribute to the array dx value. And we propagate, in iterative analysis, we propagate the properties along this slice. This example is trivial because initially all values are uniform, so iterative solver will immediately stop. Here is non-uniform slice example. We take another load. We take, just a moment, we take this one. Here is a slice. Here we can see that eventually slice reach a get global ID intrinsic call that is from non-uniform set. So this slice is non-uniform. Here is an example iterative solver. Initially, only get global ID instruction have width 1 because the instructions are processed in execution order. We will propagate on one iteration the non-uniform value to all data-dependent instructions. So you can see that the all in the final state, the all is for parameters and constants. All the rest of the slice have attribute 1. So it's a vector. And last example, control dependency, how we handle it. Here, there is a non-uniform loop condition. So if we run a wavefront, each thread iterate different count of times. And then we use the computed index in load. Here is this reversed counterflow graph. Here is the post-dominance frontier sets. We can see that for 4-body block, the post-dominant frontier is entry and 4-body. So we should consider this condition. Wait, sorry. This condition because of self-loop and this condition. I understand that nobody can distinguish the text, but I really have had short time to prepare the slides, so I'm sorry. I try to explain. Here is a fee of interest. Here is like two conditional expressions that we should add to the normal parameters of that fee. This one and that one. Because this one is not uniform, the whole slice from that load will be considered as non-uniform. here is the results. The results are very experimental, just because in HSA architecture, we cannot employ the result of analysis as we would like to do, because of restrictions that I mentioned. We get great performance improvement on a HAVC benchmark. You probably know that from the HEVC website, there is no open sale source available. So we had open sale source for the codec, and we created a C++ surrounding program, host program. So it's handmade benchmark. But on our hardware, we've got this result. Also, I ran CompuBench benchmark on AMD Kaveri platform, and I got 3 and 4 performance increase. Also, we have no more than 5% of compile time increase on a large source. Anyway, all this work is under construction. And we expect that as soon as we will be able to pass the analysis result to the machine code effectively, we will get better figures. Just because now we just scalarize load instructions, nothing else. So let's imagine we compute the load index in the vector registers. Then we can scalarize load, but we cannot scalarize simple arithmetic instructions because they have no metadata to pass through the instruction selection. And the last slide is about future work. We have an idea how to fully employ analysis result in our proprietary compiler that compile HSAIL to GPU ISA. Now we have upcoming new product, AMD GPU compiler, that fully LLVM based and will generate GPU ISA directly from the LLVM IR. And for this compiler, we decided to select explicitly vector or scalar form according to attributes. There is one pitfall because let's imagine we have a program with a high scalar register pressure. And if we just scalarize all instruction selections, we have no mean to tell the register allocator, to get a chance to let register allocator to improve. But it's still under discussion. Is this upstreamable? The answer is just below. If somebody of the community is interested, the analysis part is easy upstreamable. But we have to change selection duck builder or add some field to SD node. Anyway, we need a link from SD node to the IR or some additional field to SD node to just pass the values that we collect over the IR to selection duck. That's all. Questions, please.
Why aren't you using the infrastructure that LLVM has? So post-dominance, there is already, it's available there. So I have the impression that you build it yourself.
We initially developed like high-level compiler in LLVM to generate HSAIL. So we already had that compiler. Then we understood that we have a possibility to improve performance by means of that idea. And when I understood that I need to create a data flow and control flow analysis, the LLVM IR is a great thing to do this. It's very convenient. So Okay, the answer is we already had LLVM-based compiler backend. So.
Why are you linked with also selection DAG? Why did you put the work there? The selection DAG. So it looks like you need to work with the selection DAG for upstreaming is...
Okay.
Yeah.
Okay. Okay. I explained that we are collecting information over the LLVM IR. And then we need to apply this knowledge or in instruction selection to select the scalar or vector variant of the instruction. Or currently, we are applying it to machine code to pass it to HSAIL and then to the finalizer. So I need to pass through the instruction selection this data somehow. Because actually, LLVM, in LLVM, module pass over the machine code is prohibited. I start with this. Initially, I had an idea to create a machine pass on a machine code, but it's impossible.
I just want to mention that it is possible for some degree to do this already in the IR and pass it through selection DAG. AMD GPU already does this for loads because we can attach the metadata to the value, and the value is part of the machine mem operand. And we also annotate branches with intrinsics based on the analysis. So,
could you repeat slower and louder?
We're already able to pass some uniform information already through selection DAG because for loads specifically, we can attach the metadata to the value, which is also
memory operand.
Memory operand.
Yeah,
yes.
That's exactly what we did. Yeah, but only for loads. You cannot use this for non-memory instructions.
So you're using metadata?
Yeah. Yeah. Okay, I'm sorry. I tried to explain this. Maybe it's my fault, so nobody understands. Yes, we employ the memory operand metadata to pass the information. That's why that's why we have this restriction. So we can only scalarize loads.
And are you using intrinsics? Are you using intrinsics?
No, we tried to use intrinsics, but DAG combiner, okay, using intrinsics, we would change a lot of things in DAG combiner. We tried, but we faced with a massive change in DAG combiner, and this is not upstreamable at all. So for now, we opt for passing only for loads with metadata, and then I contact LLVM community, and one of my goals here is contact LLVM community and understand if this is interesting to somebody else. If yes, we would like to start the process of discussion to find the proper mean for passing this information. If no, we would opt for create not upstreamable change to selection DAG and keep it, and then leave downstream, so keep it in our code base.